So to find the coordinates of a stationary point or a turning point, we find the points where the derivative dy by dx is equal to 0. So in this case, we know the expression for y, so we want to differentiate y. We want to find dy by dx, and then we set that to 0. So using the chain rule, you would multiply by 5, then subtract 1 from the power, and then because this expression isn't x, it's a function of x, we need to then multiply by the derivative of 2x minus 3, which is 2. So that gives us 10 times 2x minus 3 to the power 4. Now remember, to find a stationary point, we want dy by dx to be equal to 0. So we say 10 times 2x minus 3 to the power 4 equals 0. So that means 2x minus 3 to the power 4 has to be equal to 0, and therefore 2x minus 3 has to be equal to 0. You could say, if you wanted to, the fourth root of 0, but that's a bit silly. Basically, it's equal to 0. Okay, so now we've almost found x. We just move the 3 to the other side, or we add 3 to both sides, and then divide by 3, or divide by 2. So that gives you the x coordinate of your stationary point. But the question is to find the coordinates of the stationary point, so we still need to find y. So because we know the expression for y, we can simply say, well, because we know what y is in terms of x, we can say y equals, and then just substitute the value that we found. So it's 2 multiplied by 3 over 2 minus 3 to the power 5. And that's your value of y. So that's 2 times 3 over 2 minus 3 is 0. So that's easy. So the stationary point is therefore 3 over 2, 0. And that would be your final answer for a question like that. If the question was find the coordinates of the stationary points, if it didn't ask you to find the nature of the turning point or anything like that, that would be all you need. So the trick is to differentiate and then set the derivative equal to 0 and then solve for x. So we find dy by dx, set it equal to 0, and then solve to find x. Once we found x, you can then put that x into the expression for y so that you can find the y coordinate.